All right, so far in all these derivative rules we've been looking at, the main elementary form that we've been always going back to is the power function. So we've so far I've been just dealing with power functions. X to the r. And what is the derivative for these types of functions? Well, that's the power rule. So we just bring the exponent down, keep x the same, and then subtract 1 in the old exponent. So we get r times x raised to the r minus 1. We've been doing this a whole bunch, and all the examples we've looked at so far, it's come down to this being able to differentiate this power function. Well, this is just one of our kind of elementary forms. There's a whole bunch others that we're going to be using. And so there's trigonometric, all our trig functions. So our 6 usual trig functions here: sine x, cosine x, tan x, cosecant x, secant x, and cotangent x. All 6 of them right there. And here are their derivatives. So probably the most straightforward way is just to have these 6 derivatives memorized. So derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Tan x is negative secant squared x. Derivative of cosecant x is negative cosecant x times cotangent x. Derivative of secant x is secant x times tangent x. And then the derivative of cotangent x is negative cosecant squared x. And so just a few little comments here about these trig functions. We've been talking about trig functions a little bit. They've popped up here and there in our work. But going forward, we want to really emphasize the fact that when we talk about these trig functions, the input x, is in terms of radians. So when we talk about these trig functions, the variable is variable x, or whatever variable we're using, is understood to be in terms of radians. Not degrees. So if you're using a calculator at all while you're doing some problems, make sure your calculator is set to radians, not degrees. So, and reason why this is important, really why we want to emphasize this here, is because these derivative formulas only work if x is in terms of radians. So that's one of the reasons why we primarily use radians, is these derivative formulas are nice. So derivative of sine x is cosine x. If the input is degrees, then things change a little bit. So just keep that in mind. It's an important point. It's something easy to forget. So just keep it in mind. When we talk about these trig functions, the input is in terms of radians. And then just a way to kind of remember or help you memorize these is if we're differentiating one of these trig functions and it begins with a c, then the derivative has a negative. So just to kind of keep that in mind. If we're differentiating one of these trig functions and it starts with a c, then the derivative is going to be negative. And you can kind of see some similarities here. So derivative of tangent gives you secant squared. Derivative of cotangent gives you negative cosecant squared. So there's kind of some similarities when differentiating tangent and cotangent. And then the same thing goes for, secant and cosecant. So there's a little bit of similarities here as well. The two main ones, though, of course, that we're going to be using are sine and cosine. So derivative of sine is cosine. Derivative of cosine is negative sine. So just remember, when we differentiate the cosine function, way to kind of remember it, we're kind of always bouncing back and forth between sine and cosine between these two. But when we differentiate cosine, it ends up with a negative in front. Just a way to kind of help you remember this. Now, there's also inverse trig functions that we also consider. And, technically speaking, there's inverse secant and inverse cosecant and inverse cotangent. But we primarily look at these three and really primarily look at inverse sine and inverse tan. But we have the formulas here for inverse sine, inverse cosine, inverse tan. So derivative of inverse sine is 1 over square root 1 minus x squared. Derivative of inverse cosine is negative 1 over the square root of 1 minus x squared. And again, that same kind of little memorization technique can kind of help you here. There's a derivative, or the c in front, so when we differentiate, we end up with a negative in front. And then derivative of inverse tangent is 1 over 1 plus x squared. And, like we said, there's also formulas for cosecant, the inverse of cosecant, inverse of secant, and inverse of cotangent. We're not going to use these too much. So it might be something to look up on the occasion that we do need them. We're primarily going to be sticking with these three inverse trig functions. All right, so these are going to form the building blocks of all the different functions we're going to be considering. So we have our power functions, we have our trig functions, we have our inverse trig functions. Well, there's also exponential functions. So e to the x, derivative of e to the x is e to the x. Really nice. We could generalize that. So if it's just a general exponential function, b raised to the power x, well, it's b raised to the power x times the natural log of b. So b here is a constant. Just like the number e is. E is a constant. It's a special constant. And why we talk about this a lot in calculus, you can see it right here, is e is so special, it's its own derivative. This e to the x, the derivative of e to the x is e to the x. That's one of the reasons why we use it a lot in calculus. It has the related exponential function has a very nice derivative. If it's not an e, so if it was some other constant like 2 to the x, well, it's still a nice derivative, but there's this slight adjustment that we have to make. So derivative of b to the x is b to the x times the natural log of b. So what you're seeing here, e to the x is its own derivative. Really easy to remember. Basically, you don't have to do anything. It's almost one of those cases where it's too easy, it's complicated. But when you have the function e to the x, don't do anything, and you'll be okay. And then we also have, related to exponentials, our inverse exponentials, which we call logarithmic functions. So natural log x, the derivative of that is 1 over x. If we wanted to kind of expand out our domain a little bit, natural log of absolute value x is 1 over x as well. And then for general log functions, so log base b, where b is a constant, it's still going to be 1 over x, but then there's this sort of adjusting factor, just kind of like there was for general exponential functions. So you can kind of think of this as 1 over x times 1 over natural log b. So yeah, the log part gives you the 1 over x, but then because it's a different base, it's going to have this kind of additional factor here. So, and just a comment here about natural log. Natural log, another way to write it, which we don't normally write, but another way to write natural log is log base e of x. We don't normally write that because e is such a special number. Log base e is a special function, so we give it a special name. It's the natural log function. So just a little note there about, what's going on with these different log functions that we see. All right, so that's really it. We have all of these little pieces now, all these little elementary forms that we can kind of play all our derivative games with. And so we can take all these little pieces, we can add them together, we can subtract them, we can take constant multiples and multiply them in, and now we know how to differentiate all of that by just coming back to these tables, looking up what the derivative is, and then using the necessary derivative rules. So let's try a couple examples. Let's look at the derivative of y equal to 2 times sine x plus 3 times tangent x. And when we look at this, we just focus in on, we go term by term. So there's a term here. Here's our first term. And we just focus in on differentiating that first term. So we have a constant multiple, so we know that that constant multiple stays in front. And we're really just going to focus in on the variable part here. So what is the derivative of sine x? If we don't remember, maybe we don't have it memorized yet, but let's go back to our table. What's the derivative of sine x? It's cosine x. So we throw that in. So the derivative of this first term is 2 times cosine x. Okay. Then we go on. So we're just going term by term. So we see a plus sign here. The plus sign, the addition and subtraction really kind of split our function up into all these different terms. So looking at this, we have a second term. And again, it's a constant times a variable part. So we just focus our attention on the variable part there. So we want to know what the derivative of tangent x is. Okay, well, maybe we don't have it memorized yet, so let's go back to our table. What's the derivative of tangent? Secant squared. So we throw that in. So derivative of tangent is secant squared x. The constant multiple 3 just kind of sticks in front, so it's 3 times secant squared x. And then from our sum rule, we had a plus sign. Our derivative has a plus sign then. So this is really the kind of, once you start getting the hang of these derivative rules, you're probably going to go right from this right to the answer. You're not going to show the sum or the constant multiple rule. You're just going to go right from here to here. Let's try another one. Let's try the function f of t equal to 2 times inverse sine of t plus 3 times inverse tan of t. And we want to calculate the derivative, so we want to differentiate this. Our function is named f of t here, so our derivative is going to be f prime of t. And again, when we look at this, we want to just kind of focus in on where do we have addition? And that kind of splits up, or subtraction, that kind of splits up our function into these different terms. So when I look at this, I think, okay, here's my first term. I'm going to work on differentiating that. And then I might further work within that first term and say, oh, let me look for any constant multiples that I have, and let me really focus in on the variable portion. So the variable portion here is, the variable portion here is this inverse sine of t. And then the 2 is just a constant multiple. All right, so what is the derivative of inverse sine of t? Well, I don't have it memorized yet, so inverse sine of x is 1 over square root 1 minus x squared. I'm using variable t now, so this is going to be a t here. So it's going to be 1 over square root 1 minus t squared. And I had a constant multiple 2. So my derivative of that first term gets a constant multiple 2 as well. So 2 times the derivative of inverse sine, which is ends up being 2 times 1 over the square root of 1 minus t squared. All right, so that's the first term. Then we go on, and I see I have a second term here. 3 times inverse tan of t. Again, that 3 is a constant multiple, so I really just focus my attention on differentiating inverse tan. Maybe you have it memorized. Let's go double check here. Inverse tan of x is 1 over 1 plus x squared. We're using t's, so derivative of inverse tan of t is going to be 1 over 1 plus t squared. So we throw that in. And then we had this constant multiple 3, so that's just going to multiply our derivative as well for that second term. And then we have our derivative of our first term, we have our derivative of our second term, and then in the original function there was addition in between the two, so we end up with addition in between the two for the derivative as well. So we've just done the sum rule, done the constant multiple rule. And maybe the only way to kind of clean this up a little bit, and maybe you do this as you're going along anyways, is to just take the 2 and put it in the numerator here. So you'd end up with 2 over square root 1 minus t squared. And then you could do the same thing over here. So you end up with 3 over 1 plus t squared. So again, once you get the hang of these, we have all the little pieces now. We don't normally show the constant multiple rule in our work. We don't normally show the sum or difference rules in our work. We probably just go right from our function right to the answer. Let's keep practicing though. So in part 3 here, we're going to differentiate the function g of x equal to 5 times e to the x plus x times square root x. And how we're going to do it is just how we've always been doing it. Now there is going to be something a little bit different here that we'll have to kind of work with. But let's start off. We're going to calculate g prime of x. So the name of our function is g of x, so the derivative is going to be g prime of x. Let's look at this thing. So I see an addition sign right here. So that kind of tells me it's splitting up the function into 2 different terms. So I have my first term right here. Let's differentiate that. So we have this 5 times e to the x. So looking at that, it's really a constant multiple times this variable portion. So this variable portion, derivative of e to the x, well, we just go to our table. What's the derivative of e to the x? Well, that's a nice one. It's just e to the x. So the derivative of e to the x is e to the x. Constant multiple just kind of sticks around. So the derivative ends up being 5 times e to the x for that first term. So again, one of those things, blink and you'll miss it. We differentiated here, believe it or not. It doesn't look like we did anything, but derivative of 5e to the x is 5e to the x. And that's because e to the x is this special function. All right, so then we go to our second term right here. And now we have, what do we have? We have multiplication of 2 x terms. This is no good. So we have a product of 2 x terms here. We have x times the square root of x. This is no good. We don't have, all the rules we've looked at so far have only been when we have constant multiplication or we have the addition or subtraction of 2 x terms. We don't know how to deal with a product of 2 x terms. So the idea here is to rewrite this function, rewrite this term in one of our more usual formats. And we can do this. So we can actually rewrite this. And we sometimes have to do this. X times square root x, perfectly good function, but we can rewrite this multiplication so that we get this into one of our elementary forms. Now we can't always do this, but for this problem we can. We can take this x times square root x and rewrite it actually as a power function. So how would that look? Well, x times square root x is really x raised to the 1 times x raised to the 1/2. So square root x we can always rewrite as x raised to the 1/2. And then when we have two x terms being multiplied together like this with different exponents, we can combine them into one power function where we just add the exponents. So we take exponent 1 and add it with exponent 1/2. So we end up with x raised to the 3/2. So the goal here, when we have a more complicated term like this, is to try to rewrite it as a power function. And that's what we did. So we had this x square root x, and we were able to rewrite it as x raised to the 3/2. So when we differentiate, so this function is actually equal to 5e to the x plus x raised to the 3/2. So now when we differentiate the second term now is in a form that we can actually deal with. So what do? How do we differentiate the second term here? Just basic power rule. So we bring down the 3/2, bring down the exponent that we have, keep x the same, and then if we subtract 1 from the exponent here, we go from 3/2 down to 1/2. So the derivative for the second term ends up being 3/2 times x raised to the 1/2 power. And then we had addition in between in our original function, so then our derivative just kind of inherits that addition in between as well, in between the first term and the second term. All right. So this is a good example for some of the little algebraic trickery that we sometimes have to do in order to get a function into a format that we can actually differentiate, or at least differentiate easily. Let's try the next one. And this is also going to give us another little taste of some algebraic trickery here. So our function here is h of t, which is t squared plus 1 over t, plus 7 times the natural log of t. And when I look at this, I see a fraction plus a log function. And it's this plus right here that really is kind of, at least at first, looks like this is splitting it up into two different terms. So I kind of see this as the first term that we have to deal with, and then this as our second term. And we're just going to go down the line here and differentiate each of these. Now the difficulty is that this fraction here has variables on the top and variables in the denominator. So we don't have a rule yet. We haven't seen it. There is a rule for how we can deal with division, but it turns out we don't actually need it in this case. So the idea here, and sometimes you can do this, is you can rewrite the quotient, rewrite this division again as some power functions. So kind of like what we did here. So for this first term here, the idea is we're going to rewrite this division and the way we're going to do is we're going to try to break this fraction apart so that we get some power functions. So, we're going to see when we have multiplication of two x terms, there's actually a derivative rule that helps us differentiate that, called the product rule. We're going to see that in a little bit in an upcoming lesson. But it turned out we didn't actually need a product rule to do this. We could rewrite this. We could simplify this down to just a power function. Much easier to do it this way. Same thing here. We have a quotient. we're going to learn, there's a special derivative rule that lets us differentiate quotients like this. But it turns out it's easier if we just do the division here and try to rewrite this fraction, break it up into some power functions. Much easier to differentiate power functions than try to go through more complicated derivative rules. So our strategy here is to just kind of break this up. And so we're going to rewrite this then as t squared over t plus 1 over t. And then we have our plus 7 natural log t. So this term in the denominator, I take each piece of the numerator here and we make a separate fraction for it. So the t squared over t and then plus 1 over t gives me my second fraction. All right, so now I have 3 terms to contend with. And let's keep simplifying these down, though. We want to get them as power functions. So first, t squared divided by t, well, that's just t. And then we want to get this 1 over t as a power function. So that's just t to the minus 1. So we just use a negative exponent to rewrite that fraction with a negative exponent. So t to the minus 1. And then we have 7 times natural log t. And so now, when I look at this rewritten function, I know how to differentiate each of these individual terms. Power function, look it up. You can look up the natural log, how to differentiate that. So each of these is something I can do. So now we're ready to actually calculate the derivative. And so we have now we kind of have a new first term. So what's the derivative of t? Well, there's always a hidden 1 in front. So when we differentiate t, it's just 1. We'll come back and talk about that in a second, but derivative of t is just 1. Then we go to our second term. So here's our second term, t to the minus 1. Again, this is power rule, so you bring down the negative 1, put it in front. So we're going to get minus t to the negative 2 because we subtract 1 from the exponent. So we go from negative 1 down to negative 2. We keep the variable the same. Now, originally our function has a plus sign here, but when we bring that negative 1 down, it's going to make it subtraction. So we just write the subtraction. And we just keep going. So we just keep going down the line here. Now we have our third term, and this is just a constant multiple times the natural log function. So we really focus in on differentiating the log function, the variable part, and then we'll just deal with this constant multiple after. So what's the derivative of natural log of t? Well, we go to our table. Derivative of natural log x is 1 over x. So derivative of natural log t would be 1 over t. Then our constant multiple 7 just kind of sticks along, so it's 7 times 1 over t. And then we had addition here, so our derivative has addition as well. And if we wanted to, we could clean this up. We could put the 7 in the numerator here. So we end up with 1 minus t to the negative 2 plus 7 over t. And just be careful. I know I'm guilty of it. When I'm writing t's, they start to look like plus signs. So just be careful. So there's our derivative. Let's just go back to this derivative of t. Why is it 1? Well, let's remember the derivative of mx was m. So when it's x, when it's just an x here, the derivative ends up just being the slope. So think of if we think back, this is like a line. So what's the slope of the curve? It's just the slope, m. But in terms of our process here, you can think of it as like there's a hidden 1 in front of the t. And if you really wanted to think of it in terms of like power rule, you know, t raised to the 1, when we differentiate that, bring the 1 down in front times t, and then you subtract 1 from the exponent, you get 1 minus 1 is 0. And we normally use the convention, anything raised to the 0 power is 1. So t raised to the 0 power would be 1. So if you want to think of it like power rule, maybe that's another way to kind of see why this derivative of t ends up being 1. All right, what do we got? Well, we've seen how to kind of take all those elementary forms, put all the pieces together, use our sum, our difference, and constant multiple rules to kind of, you know, play a bunch of derivative games. And let's just try one more. And we can, as we've seen, we can repeat the process. So if we have a function, we can calculate the first derivative, but then we can take that first derivative, differentiate it to get the second derivative. And that's what we're going to do here. So we're given this function s, which is equal to t cubed minus 2t squared plus 3t. And we're going to calculate the derivative ds dt. Then we'll evaluate it. Remember, vertical line means evaluated at -2. And then we'll also calculate the second derivative, and then we'll evaluate that at -2. All right, so let's start with our function s, and we're just going to differentiate it. So we differentiate it once. It's a bad squiggle. Well, okay, it's a squiggle. We're going to differentiate. So let's differentiate this function s. And that's going to give us ds dt. All right, so we just go term by term. We see we have 3 terms here separated by some subtraction and addition. So we start with the first term. Derivative of the first term, it's a t cubed. So derivative of that would be 3t squared. So just some power rule there. Then derivative of the second term, again, power rule, but a little constant multiple action going in here. So we're going to take this exponent 2, bring it down, multiply it with the 2 that's already in front. So we're going to get a 4, and then times t. And then we subtract 1 in the exponent, so we go from 2 down to 1. We don't write the 1 normally. And then there was subtraction in between, so in our derivative, there's going to be subtraction in between. And then finally, we go to our third term. It's 3 times t. So this is, again, derivative of that form mx. So derivative of that form mx is just m, the constant in front. You could also think of this with a power rule type thing. But it ends up being just 3. So the derivative of this third term is 3. There was a plus sign in our original function, so there's going to be a plus sign in between in our derivative as well. All right. So there's the first derivative. And we're interested in the second derivative. So let's just keep going. So we're going to take this first derivative and it's a brand new function. We're just going to differentiate that. So we look. This is going to give us our second derivative of s with respect to t. And we have 3 terms now, so we're just going to go term by term and differentiate each of these. So for the first term here, just power rule with a little constant multiple rule thrown in. So we bring down the 2, multiply it with the 3 that's already there. We get a 6. And then we subtract 1 from the exponent, leaves us with just t raised to the 1. We don't write the 1. Then we go to the next term. Our second term is 4t. Differentiate that. We end up, again, kind of with this similar format here. We end up with just the number that's in front. So we end up with just a 4 there. And then the negative in our derivative here ends up as a negative in our second derivative as subtraction here. And then we go to our third term, plus 3, and this is just derivative of a constant. all by itself. No variable piece here. So when we differentiate a constant all by itself, derivative just ends up being 0. So derivative of 3 is 0. So just another recollection here. Derivative of a constant b all by itself is 0. All right. And let's just simplify that. 6t minus 4. Actually, you know what? We don't normally write 0. Get rid of it. All right. So there we go. We have our first derivative. We have our second derivative. Now we want to actually evaluate. So we want to actually plug in. This vertical line means evaluate. We want to plug in t equals negative 2. Use a different color here. We're going to evaluate. So the first derivative evaluated at t equals negative 2. Vertical line means evaluate. We're just going to take this brand new derivative that we calculated, this nice new shiny function, and we're just going to plug in negative 2 wherever we see t. So we're going to end up with 3 times negative 2 squared minus 4 times negative 2 plus 3. Cleaning things up, we get 3 times 4 is 12. Then we end up with a plus 8. And plus 3, this is 23. So that's the value of our derivative evaluated at t equals negative 2. Now, we also want to evaluate our second derivative at negative 2. So we've calculated this brand new function, 6t minus 4, and we're just going to evaluate that. So we have our second derivative of s with respect to t. We're going to plug in negative 2. And so I go to my function here. Wherever I see a t, I'm going to plug in negative 2. So I'm going to end up with 6 times negative 2 minus 4, which ends up being negative 16. And there we go. So notice when we actually differentiate and evaluate, there's kind of a specific order in which we need to do things. So we differentiate first. And then evaluate second. So in order to, say, calculate the derivative evaluated at negative 2, I first have to get the derivative, and then I evaluate. Or to get the second derivative evaluated at negative 2, I first have to go through and calculate the second derivative, and then once I have that as a function, that's when I plug in. If we plug in beforehand, so say I plug in negative 2 first into the original function, I'm just going to end up with a constant. And if I differentiate a constant, I'm always going to end up with 0. So the way we actually calculate these, derivative evaluated at a specific time, or second derivative evaluated at a specific time, we first get the derivative or the second derivative, and then once we have that as a function, then we plug in. All right. So that's going to do it for our kind of our basic derivative rules. Sum, difference, constant multiple, all of our different little elementary forms that we're going to come back to and kind of use throughout. Coming up next, we're going to start talking about some of our more complicated derivative rules. Product rule, quotient rule, chain rule, some of the bigger machinery that we're going to use. And so we'll start seeing that next time. We'll see you then. Bye-bye.